Okay, oh, excuse me a minute, the stupid camera zoomed itself back again. It's a great camera, but it's kind of stupid. Okay. I don't have any control. I can't fix it. So can't hold it there. There's no option. Why in the world do they design a camera that gives me no option to use a fixed zoom? Great camera. What's the matter with these people? Okay. You guys need to be better engineers than they were. Got it? I think you will be. Of course, problem is it was a team that did this. It was not an individual. So you also got to be a better team than they were, and that's a little tougher. The team should be better than the individuals. And generally that's true if you got a well-functioning team. Okay, well, this is physics, that's not engineering, but y'all are future engineers, do things right. Good team members will be good individuals. Okay, so we have the system that we observed in lab, which schematic, we've got a beam. I'd pick it up and bring it over here, but it's on the pulley. You've seen it a bunch of times. Just our rotating beam, a couple of magnets at the end, put into a horizontal orientation of the axis so that it rotates in a vertical circle. So the tree's going to rotate in a vertical circle. We've got two, it's going to rotate this way. The way I've got it drawn, the way we did it, actually rotate this way. Actually, let's go ahead and make it as familiar as possible. We have 50 grams on one side, 70 grams on the other. Okay, that should get down to and the 0.5 meters then should be from here. Of course, the way I've got it drawn, that doesn't make sense because if it falls that far, this is going to rise that far and get into the pulley. So you can make a more accurate drawing than I did. Given the mass of the beam, masses of the magnets on the end of the beam, two magnets on the ends of the beam, familiar situation. We've got a 50 gram hanger here, a 50 gram hanger with a 20 gram mass on it here, which is 70 grams. Also 0.5 meters in about 7.5 seconds. Now you've got accurate information. You've got Audacity. You can tell me how long it took to fall down to the millisecond. Okay. That's more accuracy than we're going to have because exactly where did we have those magnets positioned? How far was the center of each magnet? Each magnet's an extended body, all kinds of things that give us uncertainties, but you've got data for the time of fall that's more accurate than anything else that we know. So I just did a count with these systems of one of you. And we both thought around 7.5 seconds. Okay. At least I thought it, and you agreed, whether that's a good team member or not. If you're just being agreeable, that's not a good team member. If you thought the same, that's great, but it's all right, it doesn't matter. Just again, you don't have to be agreeable. If you got something different, you can say it. I have no authority over what really happened. I cut my difference in yours. Okay, so the whole point is that 7.5 seconds probably has at least half a second of uncertainty in it. So there's almost 10% uncertainty in the time of fall, which is 20% uncertainty in the acceleration. 21.111. Okay. I don't think it's going to be that bad. Again, you have really accurate data for that. In this case, 7.5 seconds is the most inaccurate data. Because these masses are pretty accurate. All these masses are pretty accurate. Within 1% or 2%, of course. Not sure about the radius of this thing because it's hard to measure with the beam on it. So I kind of had to eyeball that and fill out the calipers or anything. So there's some uncertainty there. So there are uncertainties in these numbers. The 0.5 meters is pretty close. I really did get closer to 50 centimeters and 49 or 50. So as far as I can tell, this turned out to accidentally be half a meter. It's just a function where we tied the knots on the hangers. So it's surprising that should come out that nicely. Okay, so anyhow, there's our situation. And so what do we know? We know the mass of the magnets on the ends. We know the radius of the pulley. We know the length and mass of the beam. And we assume it's uniformly distributed, which is pretty much so. We know the two masses, M1 and M2, on the hanging masses. The delta SY, the displacement, 5 meters downward. Don't worry too much about that because we know things move down. The delta T, we got all that information. So now what we want to find is the acceleration AY and the final velocity VFY of mass M2. Well, that's really easy. It's released from rest. We know how long it took to buff all of that. Calculate that. Acceleration, I think, is around 2 centimeters per second squared. Final velocity, around 13 centimeters per second. So we get those very quickly. So we want to find those. And we want to write it out symbolically, then plug in the numbers and then check that against common sense. Okay. Do the calculations wrong, we find out that thing was actually moving at the speed of light. And, well, that's not it. Little common sense. We then redo our calculations. Okay, then we want to find the angular quantities. The angular acceleration of the beam, its final angular velocity, its moment of inertia. And then really what we want is its kinetic energy. And change its potential energy. It's all one system. Potential energy change. You have to identify how, where, and why. Okay, well, we want to start. We can't get this is really easy. Potential energy change turns out to be really easy. But these angular quantities are going to take a little more work. And kind of the central quantity we need to calculate the kinetic energy, once we have omega F, which isn't too hard, is we're going to need the moment of inertia of the entire system. Okay. Now, I'm going to start with the moment of inertia of the beam. Everything else, the magnets, and actually these weights have moments of inertia too, relative to the axis of rotation. And those are really easy to find. The only thing that you need to know is how to find the moment of inertia of a beam of length L rotating about an axis through its center. Now, in a little while, we're going to do an integration to find that. We're going to do an integration to find the moment of inertia of a uniform disk, and maybe learn a little bit more about what I have to know how to set up intervals. Okay. The integration technique is really easy. No fancy integration technique. You're just going to end up integrating power functions. But set up the interval. That's the key. Okay, that's where we're going right now. What's a formula for moment of inertia? And nobody seems to know right now. Okay, now I have an assignment, which I think involved, among other things, doing the integration to find the moment of inertia. Okay, so we want to make sure we understand that. So you did quite well in the assignment. But what are you taking out of the assignment? Okay, well, we'll just write down a couple of things if you really ideally would have taken out of this assignment. But number one, now I couldn't call it a rod because its beam isn't really, rod is infinitely thin. But as we'll see, when we develop the integral, we'll develop an intuition and actually a mathematical, no way to mathematically analyze how much different this beam, which is not infinitely thin, differs in its moment of inertia from the ideal formula. I don't think by more than a tenth of a hundredth of a percent. Okay. I'll give you enough technique that you could go out and prove your law on that. And if you did, that would be great, but you're probably not going to take the time. Okay. Okay, mass M. There's one more condition. Rotating about an axis through its center. You seen that before? I've written it down before. Okay. So ideally, you pick that up. Put that in your notes, a big star around it, because it's something you're going to use again. And they're going to see it in the assignment, you're going to see it in the problems, kind of sneak in. So right now, you really want to get that down. Again, we're going to do the integration and see why. It's easy. Okay. I'm abbreviating a lot, but mass M, uniform, radius R, axis through the center and perpendicular to the disk. Because a disk will naturally think of rotating about an axis through its center, so it spins, right? But we could also put an axis this way and it rotates this way around. Okay, what I have here. Okay. Talking about rotation like this versus rotation like this. The two ways the disk can rotate, and the moment of inertia, if you think it through, is clearly different. Again, you have an integral, it's not a difficult integral, but it's not a formula you really want to particularly remember because it's not going to be used that much, and you can always look it up or do the integration yourself. Okay. The ones I'm writing down here are the ones you really want to know. There are only 3 of them. I'm not including a hoop. That wasn't a disc. That was more like a hoop. It didn't. The center was missing. The moment of inertia. Well, if you got a hoop, every mass is a distance r. So the sum of the mr squared is just mr squared. All the mass m is concentrated at distance r. So the hoop just has big M, big R squared. It's the sum of all the little mr squareds. Every little m is at distance r. So you end up with the sum of all the little m's at distance big R, which is big M times R squared. Very simple. Okay. But anyhow, there's uniform disk, mass M, radius R, again, big R. as this, which is by comparison. Half the moment of inertia of a hoop. And why is it half that? Well, the reason it's half goes back to what you learned from me, okay? But the idea is simply that on the hoop, all the mass is out here at the rim. So all the MR squareds are the same, okay? With a disk, your masses are spread all the way from the rim to the center. So the average distance of the mass from the center is less. So the average of the R's is less, and the average of the R squares is going to be half. That's what it comes down to. So we'll talk about that a little bit when we do that. And what you learn from setting up and thinking about how the integral works. And looking at it graphically as well. Okay. And then for uniform sphere axis through the center, it's 2/5 MR squared, which is a little less than 1/2. Because on the average, the particles in the sphere average out closer to the center than they do for a uniform disk. And geometrically, if anybody thinks geometrically, since geometry has been effectively dumbed out of the curriculum, that's questionable. This makes the mass concentrated closer to the center. I can say more about that. I kind of want to need a bit more. So you've got these three formulas that you just cannot do without. You should be able to do the integration for any of them. One of them kind of involves some shell method, sphere. Okay. You should be able to do shell integrals. At least if you're doing engineering with anything remotely resembling a geometric object or a field with similar symmetry. Okay. You just got to know geometry. Otherwise, you don't understand what you're doing. Okay. You don't always have to understand what you're doing if you know how to use the right software and formula, but you're more limited than you would be if you knew what was really going on. Okay. Now with all that, maybe we're equipped to do this. So tell me, in terms of these symbols, what's the moment of inertia of the beam? It's going to be I beam. It's not an I beam, it's an I sub beam. Moment of inertia of the beam. You got three things: the hanging weights, magnets, and the beam, all of which are effectively rotating about the center of the, yes, these things aren't actually rotating, but they still have moments of inertia. They act very effectively as though they were rotating. And we'll talk about that a little bit. Okay. So there's those symbols. What's I sub V, what's I of the magnets, and take at least a shot at the eye of the hanging weights. Now that's pretty good. Oh, it's pretty much chalk. Okay, little chalk. Okay. Moment of inertia of the beam. Well, I just kind of gave that one away. Okay, but in that moment of inertia of the magnets, well, actually, I think somebody used R squared because that's, of course, your formula for mass of particle, right? Well, each magnet is pretty much a particle. It's pretty much all concentrated close to the center. You had the magnets turned this way, lengthwise, so they'd be even closer to the center. Of course, some parts of the magnet were a little further from the center of rotation than others. That isn't a huge difference. And there are actually formulas you can use for that. Okay. But for right now, we're going to say, okay, moment of inertia of the magnets is both at the same distance from the center mass, distance factor of 2 on the moment of inertia of one of the magnets. Moment of inertia of one magnet is mass of the magnet times L over 2 squared. Whatever you might have had an R there, which is not a bad instinct, but R has a specific meaning here. It doesn't have anything to do with how far those magnets are. Okay. You want to be careful. Okay, well, I looked at it. Yeah, that looked good. But when you think about it, you got to use the right distance. Okay, the hanging weights. For now, I'm not going to go into the reasons for it because it takes math to at any instant. I said I wasn't going to go into it. I'm just going into it. The line of this force, the line of gravitational force of either one of these magnets is a distance, little r, 3 centimeters in this case, from the axis of rotation. Okay. So it's going to have a moment of inertia. It's the same as if at this instant, the magnet was sitting on the edge of this disk. Okay. That magnet, this mass. Now, of course, this is an extended mass. It wouldn't fit on the edge of the disk, but just concentrate this mass down to a particle, put it on the edge of the disk, and its moment of inertia is the same as it would be on the edge of the disk. Now, a short instant later, what I just said is still true. It's as if this mass was at the edge of the disk, even though the disk has rotated a little bit. It's like this mass stays at the edge of the disk because its moment arm relative to the axis of rotation is unchanging. It's always as though it's at the edge of the disk in this direction, this edge of the disk. Okay, and the same with this. So you kind of, if that image makes any sense, it kind of helps to understand it. It's still kind of subtle. It takes some pondering and some getting used to the idea. But that's going to be then plus M1 R squared plus M2 R squared. And of course, so wrote it as M1 plus M2 times. At the time I looked at it, we weren't sure what we we're going to put there. But you know, these masses are both at the same distance. They're moment arms are the same distance from the axis of rotation. So it's safe to do an M1 plus M2. But they're separate. So might be safer to write this out and then factor. Okay, well, there it is. Bingo, you got the moment of inertia. Okay, so we want to find the kinetic energy. Before you find the kinetic energy, my hint is solve the uniform motion. The uniform motion, the uniformly accelerated motion, we're assuming it's uniformly accelerated. And your data will probably show that the angular acceleration of that beam is uniform. So we're going to assume that's the case. And if it varies much from uniform, then the fault's going to either be with your data or your analysis, because I'm about as sure as I could be that you're going to get a uniform acceleration system. As far as sure as I could be about any actual physical system, which is always subject to gremlins. Okay. Okay, well, what do you need to find AY and VFY? Write it out in symbols. Okay, we're going to move on. Y'all are right on track with this. What's AY? What's VFY? Well, we can say that delta SY is this. Now using, I've written T instead of delta T. A lot of you have written a delta T, so I'll put a little tiny delta in there. Okay. But I can't read it. Okay, so we can solve for AY. It's a quadratic equation. It's a mess to solve for AY. So you probably don't really want to do that, except you can in this case, because V naught Y is 0, which eliminates the B term or the B factor in your quadratic formula. And in the case where this is 0, you can get this, right? Okay, so that's actually pretty simple. And then you can get VFY. VFY equals V naught Y plus AY times delta T squared. And if you multiply this, it's not times delta T squared. That's going to cause real problems with the units. Okay, realize that as soon as you weren't going to have a delta T. If it's AY delta T squared, then the delta T squared goes away and your acceleration is just a distance, right? Or your final velocity is just a distance. That wasn't so far. But anyhow, that's this, right? Now, if I was thinking this through, I wouldn't bother a bit with the equation of motion. As I said before, VFY, since you're starting from rest, is equal to double your average velocity. Take double your, so VFY is going to be change in velocity. Divide that by delta T and you get quick and dirty. Okay. So there's a reasoning sequence there that I've used before. It's symbols. You can write this out immediately without having to think about the equations of motion. And it's a deeper insight than just plugging into the equation of motion. Now, y is VFY equal double Vy bar. Because you have a linear graph of Vy versus T. So the average is the halfway, which is half of the final. We talked about that before. I really recommend that you understand that, because you can quickly think through. Now, if you don't have, good arithmetic skills. Yeah, I used to. Sometimes I still. Okay. Yeah, go ahead and rely on your equations, but it serves as a check. Intuitively, you're following 50 centimeters in 7.5 seconds. Okay. Well, 5 over 7.5 is 6. Okay. And you do just a little mental arithmetic and you find that you're moving at about an average of 6 2/3 centimeters per second. Initial zeros, you can double that to find the final because of this, but because you can always do that. Okay. And you get 13 1/3 centimeters per second final. You divide that by 7.5 seconds, you get a little less than 2 centimeters per second. Then you divide 13 1/3 by 7.5. Okay. What's that? It's 40 thirds divided by 15 halves. Okay. 120 divided by 5. Okay. Didn't come out, but working memory. Okay. Write it out. Quick and dirty solution. So you get everything just reasoning this. Then symbols. Change in velocity is your final velocity. Again, since your average initial velocity is 0, we started this from rest, make it simple. And that's just a calculation I did in my head. You divide 50 centimeters by 7.5 seconds. You get the average velocity, double that, you get the final velocity, double that by your delta T. Again, recommend it, but this works fine. Okay. This is a little more complicated and a little less intuitive. You're just using formulas rather than thinking through something you can easily think through. So I do recommend thinking it through. Okay. Either way, we can now plug numbers in and get our acceleration. Okay. So we kind of got this checked off. Kind of got this checked off. How about a change of potential energy? You write down what the change of potential energy would be, again, in symbols. Okay. I think everybody's either there or on the verge of being there. I think what you got to identify first. Yep, there's a focus. Okay. At least this is in focus. We'll see if I can focus. Physically, probably am. But okay. Change of potential energy is what? Well, this is going up, so its potential energy increasing. This is going down, so its potential energy is decreasing. It's all gravitational. If there was a spring or a rubber band in here someplace, well, things would get a little more complicated. Okay, you could have a spring being stretched or compressed as this thing rotates. You can build all kinds of group Goldberg contraptions and figure out the potential energy change. But in this case, now on the beam, anything that goes up on one side is going down on the other. For any particle that's moving up here, there is a particle at the opposite position that's going down. Okay. For every mass increment over here that goes up, there's a mass increment over here that goes down by the same amount. So there's no potential energy change over here. Potential energy change is then just going to be well, I'd like to write out delta PE of mass 1, delta PE of mass 2, but it'll be this. So it's going to be M1G delta SY, because the force, the conservative force is M1G, and delta SY is in the direction opposite gravity. And remember, the change of potential energy is equal and opposite to the work done by the conservative force. Okay. It's equal and opposite to the work done by conservative forces. So for M1, gravity is M1G downward, delta SY is upward, so the work done by the conservative force is negative, so potential energy change is positive. Now, if you just use an MGH, gotta be a little careful about signs, and you really should understand that in terms of this definition of a change in potential energy, because when we get into gravitation, electrostatics, it gets a little more confusing. And if you don't have this down, if you're just thinking MGH all the time, it's not going to work for you. And we will be getting into gravity just after Thanksgiving. Okay. Okay, so that is the correct expression. I think everybody either had it or was on the verge of it. Okay, there's potential energy change. Well, that ought to be equal to the kinetic energy change. How are you going to get the kinetic energy? So they've got LSD. So to get the kinetic energy, you better know omega. I hope you're used to the idea that kinetic energy of the rotating system is 1/2 omega squared. This is 0. So how do we find omega F? Okay, now we had a series of observations. Okay, first said, divide the speed by the radius to get the angular velocity. Said speed of what? Well, the answer was speed of the descending masses. They're pretty good. And the radius of the pulley. Why? And another first answer, well, it's because the rim of the pulley is moving at the same speed as the descending masses, assuming that the thread isn't slipping. And from our tactile experience, incidentally, when we did the experiment, said we should be rotating functions. Okay, I don't think everybody had their hands in the string. I think people kind of got into their function, did an excellent job of it, and went smoothly. Would have probably gone less smoothly if you'd been rotating, but you would have had more tactile experience of the whole system. Okay. So I do kind of recommend that, play around with the system a little bit, get the feel of every part of it. So anyhow, that aside, is a good answer. So we determined that, okay, yeah, the rim of the pulley is moving at the same speed as the descending mass. And the whole blame system, except for the masses, are locked to the pulley. So they're rotating at the same speed as the pulley. So omega F equals what? Remember, the pulley moves at speed. Equal to that of the hanging masses. There's your central observation. Omega is VF over R. Remember, R has only one meaning here. Okay. Probably should have put an R pulley on there or something, a subscript, because sometimes we do want to use R for something else. But I didn't. But it would have been better if I had. So just kind of think through when you assign variables, how R might be used otherwise. Okay. And it would have been better if I had used a subscript. I did. So omega F is VF over R. Well, for simple calculation, you use this, but this tells you more about what the thing really means. This is a simpler algebraic form. This is a form that connects this to all this. Okay. Okay, well, that's pretty good progress at this point now. What's our last question? Okay, well, assuming we have only conservative net force. And that's pretty much so within the system. Now, there are internal forces in the system. Okay. You know, you have centripetal forces on those magnets holding them in, but that's internal to the system. On the system as a whole, you have only gravity. So the delta KE should equal delta PE. If we're going to ask you to take your own data, and you can use 197 grams if you want to. 200 grams is going to be close enough. And round off your time to three significant or three decimal places. That's overkill, as I talked about earlier, but just be safe. Use these masses, and you have an expression for delta KE. You have an expression for delta P. They should be equal within limits of experimental uncertainty. I would say they should be equal within plus or minus 2%. The only thing that isn't plus or minus 2% is this. And these things can vary a little bit. It might be safer to use 197 grams, just do a little spreadsheet or something. So you can change your variables, you know, use cell references and all that stuff. Set it up sensibly, in other words. So you can just change one cell and everything else changes. You can and I assume that you know that much about Excel. If not, ask me. Sit down at the computer and make sure you do. I'll demonstrate that at some point. Most likely, except for those little tricks, you know more about Excel than I do, because I really don't like Excel. But I have to admit it's powerful and handy, and the whole spreadsheet setup is informative, even if it was written by accountants and people don't understand the order of operations. Or ignore it. Yeah, be careful about order of operations. My preference is write a program because everything is intelligently as possible. That takes long. Okay, good. Now, let's talk about integration and moment of inertia, which is really a simple exercise in second semester calculus. Okay. Here's what we're going to do. Mass out, got a length out. Okay, so we're going to water again. And we're going to subdivide it into a bunch of little increments. What you do, you partition in a bunch of sub-intervals each of length L over M. Okay. Now, here's interval number 1. Here's interval number N. Here is interval number I. What's the moment of inertia of interval number I? First of all, delta I sub I, delta big I sub little I. Is M sub I R sub I squared. Okay. Now what's R sub I and what's M sub I? Well, M sub I should be easy. So tell me what M sub I is. So M sub I big M over little m. Big M over N. Okay. What's R sub I? And I'm going to use an R sub I star. Well, what you do when you do an integral is you do a sample point, an arbitrary sample point. You have position. Well, we're doing this in terms of R. Okay. So R is our variable. Should have stated that earlier. Yeah, we're going from R equals 0 to R equals L. Okay, what's the position of the ith interval? Well, think about it. It's I over N times the length, right? Now there's, if I is 1/2 of N, then we're halfway there. Now I'm glossing something over, okay? I'm doing what physicists do with calculus. And I'm more mathematician than I am a physicist, but it doesn't really trouble me that much anymore. Okay. Kind of glossing over a little bit of the theory. But R sub I star. I is how many of these little increments we have, N is how many there are. So I over N is the proportion of the total length that we span here. Okay, so okay.
Yeah, we got.
Well, the sum of M over N R I squared. And actually, I don't really need this. I could use this along with a little bit of theory of sequences, sum of quadratic sequence. I'm just going to say that this approaches, since we're out of time, the interval 0 to L of and I haven't made that connection very well. Because they're effectively integrating R squared, we get R cubed over 3 evaluated from 0 to L, giving us 1/3 ML squared. And then we're out of time. I'll just say it briefly. We'll come back to it. If I'm rotating about the center, then R is just the distance from the center out to the increment. For every increment on this side of the center, there's an increment on this side of the center. So the R's just go from 0 to 1/2 L. Okay. So we would end up integrating from 0 to 1/2 L. They're only divided by half as much, and in terms of mass density and so forth, I don't have time to do that. So I kind of shortcut it a little bit. Look at what your text tells you. On the average, your R's are all going to be twice as close because you're rotating about the center. So your R squared is going to be 1/4 as much. And 1/4 as much as 1/3 ML squared is what? 1/12. Okay. Now your book, your MyLab, that does a nice job of showing that connection in terms of energies and so forth. So it's well worth looking at.